Standard electrode potentials. What is this? All substances in their standard state, 1 molar. Okay. So, um, when we did the lab, right, we were testing for iron in food. We used permanganate. Now, iron 2's already lost electrons, right? So, it's hard to take electrons off of something that's already lost electrons, but you can still take a third electron off of iron, right, to make iron 3. And the substance that can do it is permanganate. Right, so if we use our oxidation state rules, we see that permanganate, when we add up the oxidation states, comes out to be +7. All right, so that's something that's hungry for electrons, right? So permanganate is a strong oxidizing agent. So it's able to take the electron away from iron 2 to make iron 3. Okay. The way we can think of this reaction is as two half reactions. I guess that's a word. So we can split redox reactions up into an oxidation half reaction, all right? Something losing electrons like a metal, right? Zinc losing 2 electrons, or reduction, something gaining electrons like H plus ions, right? They want their electrons back to form hydrogen gas. So when you add the two together, right? The electrons going in have to equal the electrons coming out, and you get the overall redox reaction. So I can look at a standard reduction potential table. What's that? Well, it's just a list of reduction half reactions, right? So here it is. Here's permanganate taking 5 electrons to turn into manganese 2. And here would be iron 3 taking an electron to turn into iron 2. So what I can do with these half reactions, right, they're both reductions, right, taking electrons, is I can recognize that because permanganate, right, on this side of the chart, these are the takers, right? Anything that is above a reducing agent, these are the givers on this side, the reaction is going to happen. So permanganate can take electrons away from all these reducing agents that lie below it. Here's chloride, right? The only thing chloride can do is lose electrons, right? So permanganate is something that's strong enough to take electrons away from chloride to make chlorine gas. It's also strong enough to take an electron away from iron 2 to turn into iron 3. So if I want to make that a oxidation half reaction, I just flip it around, right? So instead of iron 3 taking an electron, it's iron 2 losing an electron to become iron 3. Now the number of electrons going into the reaction have to equal the electrons coming out. So I multiply the top half reaction by 5. So this reaction is transferring 5 moles of electrons. That's going to be important for us in this topic. So when we add these two half reactions together, right, the electrons going in and the electrons coming out cancel, right, anything that's redundant, and I get my overall redox reaction. So adding half reactions together can give you the overall redox reaction. So I can just look up, redox half reactions, reduction half reactions, and spin one of them around and make redox reactions out of them. Now, the thing we've been ignoring are the numbers over on this side. These are what are called reduction potentials. And what it means is how much of a push the electron has when the oxidizing agent takes it, right? It's measured in volts. That's what volts is. How much energy does this oxidizing agent pull, right, when it pulls an electron? So we look at this, right, 1.78 volts versus 0.77 volts. So what this is telling you is that permanganate is a better taker of electrons than iron 3, right? It has a higher reduction potential. A reduction potential is defined as the tendency of a chemical species to be reduced by gaining an electron. It is defined in reference to hydrogen, right? Which is decided in the scientific community to have a reduction potential of 0. So it's a relative thing, right? Reduction potential. How good a taker are you? Well, we're comparing to, in this case, hydronium ion, right? H plus ion, hydronium ion, the same thing, which is given a reduction potential of 0. So anything that lies above hydronium ion on the chart is a better taker of electron than hydronium ion, right? And it'll take electrons away from, it's changing here, hydrogen gas to form hydronium ion. So it's arbitrary, right? It's decided that, H plus ions taking electrons is going to have a voltage of 0 volt, right? Joules per Coulomb, right? It's how much push the electron has during the redox reaction. So, take the electron, right? How much do you pull on that electron? So what I can do with these reduction potentials, right? So if I spin the reduction potential for iron 3 around and make it a oxidation half reaction, so right now it's a reduction half reaction, reduction potential. If I spin it around, now it's an oxidation half reaction, and I change the sign on the reduction potential. Now it's an oxidation potential. So everybody see that? It's positive voltage. It's a positive reduction potential. So this is how good iron 3 is at taking electrons. This is a measure of how good iron 2 is as giving electrons. Hey, like we thought, right? Iron 2 is not going to be too good at giving electrons. So what I do is, right, when I balance the electrons, hey, notice when I multiply that half reaction, or that half reaction by 5, it didn't do anything to the voltage, right? The oxidation potential is these potentials are intensive properties. It doesn't matter how this is balanced. So when I add these together, right, get my 5 moles of electrons transferred and get my overall redox reaction, if I want to get the voltage for this reaction, right, how much push those electrons have going from the iron 2 to the permanganate, I just add the oxidation potential to the reduction potential and get the overall voltage for the reaction. So nice, right? This seems a lot like Hess's law when we're dealing with heat, right? So it's similar, right? Add these half reactions together, add the voltages together to get the overall voltage. So just as the sum of the overall cell reaction can be thought of as the sum of 2 half reactions, the standard voltage can be thought of as the sum of the potentials. So if this is a reduction potential, spinning it around makes it an oxidation potential, and you change the sign in order to make it an oxidation potential. So I don't need a list of oxidation potentials. I've got a list of reduction potentials, so I can get the oxidation potential for the product. Add the oxidation potential to the reduction potential to get the voltage for the cell, right? That's the redox reaction. So when we talk about electrolytic cells, right, we're separating the oxidizing agent from the reducing agent when we do the reaction. So we've got iron on the one side, iron over here, losing electrons to silver plus over here. So we make the reaction happen through a wire. All right, and in this way, we can harness that energy, that push on electrons to do work, right? Move the voltmeter in this case. So which electrode is the cathode? Okay, so we did this in the last video, right? The cathode is where reduction is occurring, right? Red cat. So by convention, the cathode is on the right-hand side, but look at where the electrons are moving, right? That's where the cathode is, right? So I don't know, used to on the AP exam, they switch these around sometimes. So you want to look at where the positive voltage is occurring, right? So silver plus is the taker, iron's the giver, the electrons are running over to the silver plus side. Red cat. How would you determine the standard voltage? EMF is voltage, electromotive force, generated by this cell. So I'd use my reduction potential chart, right? I'd look up what the EMF or the voltage is for silver taking an electron. I'd look up what the voltage is for iron 2 taking electrons, recognizing that if I flip it around, I get the oxidation potential for iron. So silver is taking electrons away from iron. So I flip the reduction for iron 2 around and make it the oxidation potential for iron. And then I can add these two half reactions. Oh, got to balance, right? 1 electron going in, 2 electrons coming out. So multiply that top half reaction by 2 to get the right number of electrons going in and coming out. When I add these together, I can add the voltages together to get the overall voltage for the cell. How would you determine the standard voltage generated by, we did this, right? So there's the voltage. 1 molar concentrations. This is important, guys, right? So whenever we're doing a, did I skip that? When we're doing a, figuring out the voltage for a a standard voltage, the species that influence the position of equilibrium have to be 1 molar or 1 pressure if it's dealing with a gas. Let me see if I did that, because I wanted to mention that. I was very, very impressed with that. There we are. I missed this. So this was a more complicated one, right? But everything has to be 1 molar in this scenario, right? If I'm going to get a voltage of 1.01 volts, I have to have 1 molar concentrations of the species that can affect the position of equilibrium. So this is a spontaneous reaction, right? We're going to have a positive voltage here, right? We're going to use up that iron 2. So this is a point in time during the reaction. We talk about standard conditions. This is a 1 molar condition. I expect when this reaction goes forward that this concentration of iron 2 and permanganate are going to go down, and the concentration of the iron 3 and the manganese 2 plus are going to go up. By the time I get to equilibrium, I expect this to be close to nothing and this to be, at its maximum. And at that point, I expect the voltage of this reaction to be 0. So when we talk about standard conditions, right, we're at a particular point during this redox reaction, 1 molar concentrations. The voltage is going to change if we change the concentration. And that's going to be the next video, right? Non-standard conditions. So it's standard conditions, it's 1 molar concentrations of the reactants and the products. Anything that's affecting the position of equilibrium. All right, a voltaic cell similar to the one shown in 20.5 is constructed. All right, so we did this, right? We've got silver plus taking electrons away from iron. What is being oxidized? What is being reduced? Okay, so the silver plus is the thing being reduced. The iron is being oxidized. Write the half reactions that are occurring at the 2 cells. All right, so, right. The anode, I'm going to have anox, oxidation occurs at the anode. I'm going to have iron losing electrons to turn to iron 2. And over at the cathode, on the other side of the cell, I'm going to have reduction occurring, right? Silver plus taking electrons to turn into silver. So again, right, the beauty of a voltaic cell is you just make the redox reaction happen through a wire. So the electrons are pushed through that wire. Indicate the signs on the electron. So guys, the negative sign goes to the anode. All right, so this is where the electrons are emanating from, right? They're coming off of the iron and going over to the silver plus. So the plus side of the reaction is the cathode, and where the electrons emanate from, right? The electrons are going in this direction. This would be the negative side of this this cell. So the electrons going this way. This is the negative side. This would be the positive side. E, do the electrons flow from the silver electrode to the iron or from the iron to the silver? Well, they flow over from the iron, right? So this is what this looks like. We start out with a certain concentration of iron 2 and silver plus. It doesn't look like we're at standard conditions here. So we have a fresher battery. So the electrons start being pulled off of the iron. They push the voltmeter, right? The push on the electrons moves the voltmeter, and they go over to the cathode, where the silver plus takes the electron. Oh, there we go. So iron lost the electron, it turned to iron 2. Silver plus takes the electron and turns into silver. So as this reaction goes forward, the concentration of iron 2 is going up, the concentration of silver is going down. The chloride ions are running in the one direction to balance the charge on the anode side, which is building up a positive charge, and the potassium ions run over to the cathode side, where I'm building up a negative charge, right? Those nitrates don't have a corresponding cation, so the potassium ions balance that, and we keep the electrons flowing, and they flow, and they flow, as long as we've got silver to take the electrons. The more positive the value for the potential, the better the oxidizing agent. Right. So the best oxidizing agent on this chart is fluorine gas. The worst would be lithium plus. So therefore, the best reducing agent would be lithium metal. So if I want a big voltage, get a really good taker with a really good giver. and this will give me a large voltage at standard conditions.